Okay, so today we're going to finish up section or chapter 3, the rest of section 2 in chapter 3. And our objective is we want to be able to tackle some problems where we're figuring out what the equation of the line is without actually having a data set. So, another thing that we could talk about, your least squares regression, right, can also be called your least squares regression line, can also be your regression line or your best fit line or your prediction equation or whatever you want to call it. But there are times where you aren't given the data set. So I'm going to read this problem and then I'm going to explain all this stuff to you. Okay, so researcher used data from a random sample of 15 high school students to investigate the relationship between foot length and height. The mean and standard deviation for the feet were 24.76 and 2.71 respectively. The mean and standard deviation of the heights are this and this respectively. It gives us the correlation coefficient between foot length and height as r equals 0.697. Now we want to find the equation of the regression line for predicting them. So what we need to talk about is this should be y hat, okay? This equation here, b equals r times standard deviation of y over standard deviation of x. This is on your formula card, okay? And I just told you what they are. And what we also need to know is that y hat equals a plus bx always passes through the point x bar comma y bar, which means, and I wrote about this on my key, that every y hat line passes through x bar comma y bar, every single one. All right, so when you read this problem and the method I'm about to explain, you only do if you're given the averages of your x's, the averages of your y's, the standard deviation of your x's, and the standard deviations of your y's. Okay, so the first thing you do is you find b. It's r times standard deviation of y over standard deviation of x. I plugged it in and I got my b. So then the next thing is, this is what we know. We know y hat equals a plus bx. But what we could do is we can plug in y bar and x bar for the x and the y, right? And then that lets us do, here's our y bar equals a plus, here's the b we just found in the first step, times x bar. And when you solve this for a, you get 103.34. So that means that now you can plug it in. Y hat equals a plus bx. Here's the a we just found, plus here's the b we found in step 1, x. So really, it's just a bunch of algebra, okay? The statistics part is understanding the vocab in the problem, all right? Again, this B equation is on your formula card, and I would need to look again, but I also believe that this y bar equals a plus bx bar, I think this might be on your formula card as well. Take a look. I think it might be on there, okay? You only do this process if you're given this information. Otherwise, don't, because you don't have enough information. All right. So last thing we need to do is we need to talk about r squared. Your r squared is your coefficient of determination. Okay, be careful. R is called your correlation coefficient. R squared is called your coefficient of determination. All right. And this measures the proportion or percentage of variation of your response or your y variable that's explained by your regression line. And your textbook has a great little tip on page 181 explaining this. So here's what we're going to do. Okay, if you are given r squared is this, it means that 3.57% of the variation in y, whatever your y is explained by the least squares regression on whatever your x is. Okay, you're going to use this general statement that I put in these brackets, right, to describe r squared, but you're going to plug in, like whatever the r squared is, plug in that number, take out the letter y, put in whatever your y variable is in the context of the problem, take out x and put in whatever your x is in the context of the problem. Okay, and I explain this in part D on the problem on the next page. So that's r squared, and we'll come back to this. All right. The other thing we can do, and our last objective for this chapter, is we want to be able to compute and interpret the standard deviation of your residuals. Okay. You've got this. When I converted it from Word Docs to Google Docs, it went all wacky. I'm sorry. So S is your standard deviation of your residuals. If you're asked to interpret it, it tells you the approximate size of our typical prediction error, how far off our residuals are going to be. Okay, it's how much, so you're going to write how much you're typically off by. Okay. When you're looking through number 8, okay, football coach looks at the relationship between the average number of points scored per game and the number of wins Y for 12 football teams in the Southeastern Conference. They're giving us the least squares regression line, S and R squared. Okay, they gave us our scatter plot, and this is kind of small to read, but it gave us our residual plot. So first, we want to calculate and interpret the residual for South Carolina, which scored 30.1 points per game and had 11 wins. So to calculate your residual, you're first going to figure out your predicted, plug in 30.1. So your predicted Y is 9.4. Residual equals AP, actual Y minus predicted Y. There's your residual. Don't forget the problem asks us to also interpret it, which means South Carolina won 1.6 more games than expected. All right, now part B, is a linear model appropriate for these data? Explain. The scatter plot looks linear, good, and the residual plot has even scatter. There is no U-shaped pattern. So the residual plot has no pattern, or you could say has random scatter, which indicates that the original data is linear. Good. Okay. Now we want to interpret the value of S. So S is our standard deviation of our residuals. So we want to figure out how far off we are. So I write that here. When using the least squares regression line, we will typically be off by about 1.24 wins when we use it to predict. Okay, and I got the 1.24 because that's what my S was. That's the standard deviation of my residuals, how far spread out they are from the line. And then R squared is 0.88. So we want to interpret the value of R squared. So this is where I'm using that sentence up here. Okay, what percent of the variation in fill in your Y is explained by the least square regression line on fill in your X? So about 88% of the variation in wins, which was my Y, is accounted for by the linear regression equation on fill in what your X is in the context of the problem. All right. So your bookwork has lots of good practice on this down here. So here's what we got. We already talked about outliers, right? It's completely away from the overall pattern of the data. But you also can have this, a high leverage point. High leverage point is a vocab term that's relatively new in statistics land. So this isn't actually in your textbook, but it's now in the AP curriculum. So it's when outliers are horizontally far away from other points. So let's say I graphed all of your ages, right? You're all in the 16, 17, 18. Well, I'm in the upper 30s. So horizontally, I'm far away from you guys. I might still be in the form of a line, right? I might be really high, so I might be really far and really high in the data set, and you guys might be on the left and low. So we could still maybe form a line, but horizontally, I'm really far away from you. All right. Influential observations are ones that strongly affect your regression line. If you're removed, then they change the relationship substantially. Okay. Both outliers and high leverage points can be considered an influential observation. All right. So it could totally change the slope. It could totally change the y-intercept. Anything that totally changes your correlation coefficient or the relationship, any of those types of things can all be called influential observations. An outlier is considered an influential observation. A high leverage point can be considered an influential observation. And have a good day.